So today we take a look at our inverse trig functions, specifically the graphs of our inverse trig functions. It's important to understand, again, that mostly you just have to recognize these. You don't have to reproduce them very often, but occasionally. So that's what we'll do today. All right, so what you need to do first on a piece of graph paper is graph your parent, sine x, from negative 2 pi to 2 pi. Now, when you look at this graph, we're going to talk about inverses. So go to your cumulative notes, just as a reminder that we have done inverses before. In Unit 2, Function Basics, Day 6 or 7. Let's see. We have finding inverses algebraically. So a reminder, finding an inverse, we switch x and y and solve for y when we're dealing with it algebraically. In a graph, we still switch x and y, but you need to remember that only one-to-one functions have inverses. So they need to pass the horizontal line test. That's our test for one-to-one functions. Now, we also reflect over y equals x for an inverse. And just a reminder from our basic function material, if I look at x squared, it doesn't have an inverse because it's not one-to-one, so I had to restrict the domain. I erased or ignored a part of it in order to create an inverse. That's the same thing we're going to do with our trig graphs. Math is consistent, so it was a nice little review. Okay, so going back to our parent, sine x, again, this is why you grabbed graph paper, so you can graph that first. If you look at it, it certainly is a function. It passes the vertical line test, but it fails the horizontal line test. It is not a one-to-one function. So what we need to do is imagine erasing or ignoring a good chunk of this graph in order to make it one-to-one. A mathematician a long time ago decided that with my sine curve, if I only look at the piece from negative pi halves to pi halves, that is the piece of my sine graph that is one-to-one, and that will indeed allow me to find the inverse of my sine. So the domain of that graph is from negative pi halves to pi halves. The range goes from negative 1 to 1. So if I take that graph and I take the x values and y values and switch them, because that's what an inverse is switching x and y, the points really don't change much. So what you need to imagine is that reflection over your y equals x line. And so now I'm graphing in the inverse of sine x. That is my inverse of sine graph. We could call it x equals sine y by just switching x and y. Or we could use our good inverse notation. Y is the inverse of sine of x. That is not a reciprocal. You saw reciprocals yesterday. It's an inverse. So there is my inverse sine graph. I'm going to use a highlighter to try to show it off a little bit more. Again, most of the time, there's my original, y equals sine x in yellow. My parent graph, if you would. And then I'll color code for my inverse graph. Again, like the reciprocal trig graphs, you mostly just have to recognize the shape in a multiple choice question on a Regents exam, but be able to reproduce it because I might ask you to reproduce it. Restrict your domain, switch x and y, and go from there. So here my pink graph, I didn't really like the green, is my inverse sine graph. Okay, so moving on to cosine. There's my cosine parents from negative 2 pi to 2 pi. Use the graph paper you picked up on your way in to create that. Again, my cosine graph is a function, but it is not one-to-one. It fails the horizontal line test. So again, we need to pick a part of the graph that will make it one-to-one. We have to restrict the domain. There are other places, however, mathematicians a long time ago decided that they wanted to look at this part of the graph from 0 to pi. So we're going to restrict the domain on my cosine graph to 0 to pi. The range stays from negative 1 to 1. Reviewing domain and range from the beginning of the year. So now if I look at these points on my graph and I switch the x and y values, here I went 0 up to, so if I go over to 0, there's a point on my inverse graph. Next I go over 3 up 0, so I'm going to go up 0 or over 0 up 3. And if I go over 6 blocks and down 2 blocks, then I'll go left 2 up 6. Again, switching x's and y's, thinking of it as a reflection over y equals x to determine the shape, because sometimes these are a little tricky. And here is my inverse cosine graph. Again, I'll take a highlighter to emphasize which one is my inverse. Again, because it's an inverse, I switched x and y, so I could simply call it x equals cosine y. The problem is we can't graph that because everything we graph is a y equals, so I'm really going to call it the inverse of cosine x. Y equals inverse cosine x. There we go. Finally, for tangents, I've drawn my parent graph with the asymptotes. Once again, tan itself is a function. It is not one-to-one. It fails the horizontal line test, so I need to restrict the domain. This one I feel is a little bit more obvious. If I just look at the chunk of the tan graph that's between the first two asymptotes, negative pi halves and pi halves, that by itself is a one-to-one function. So that's the part that I'm going to reflect over y equals x, or find the inverse of. So the domain is from negative pi halves to pi halves. Notice there's no equal to sign. The asymptotes are at negative pi halves and pi halves. The range is all real y's. So we switch x and y, including the asymptote. So I go from vertical asymptotes to horizontal asymptotes. On this scale, my asymptotes were 3 blocks out, so I'm going to go 3 blocks up and down for my horizontal asymptotes. And then again, I count blocks to switch my x and y values. 0, 0 stays put. Here I went over 1.5 and up 2 blocks, so I'm going to go over to up 1.5. Left 1.5, down 2, reflects to down, left 2, negative 1.5. And again, if you imagine reflecting it over the y equals x line, it helps you get the shape of your inverse tan graph a little better. And there it is. So again, these look weird. Math is consistent. Fortunately, most of the time you just need to recognize the inverses and reciprocal graphs, but do be able to reproduce them. We could call it x equals tan y. Better notation is y is the inverse tan x. Now the last thing I need to mention to you is there are other symbols for finding inverses that you may come across, and I just need to show those to you in case you come across them. You need to understand that they're all the same. So if we talk about the inverse of sine, we could call it x equals sine y, switching x and y. Better to call it y equals inverse sine x, using inverse notation. Sometimes, however, you'll see the word arc. Arc means the angle that measures. When you see y equals arc sine x, either lower or uppercase, that also means the inverse of sine. We usually don't see that with graphs. We usually only see it with solving equations. We'll go over those in class. But today I just need you to recognize that those are synonyms. So all 4 of those expressions mean the inverse of sine. And we can do the same with cosine and tangents. We can find inverses of cosine and tan using the same notation. We could switch x and y. We can use our inverse notation, which is what I prefer. And we can use little a arc or big A arc. Now you do need to understand that little a and big A do have little differences in meaning, and we'll talk about that in class. But for tonight, I just want you to recognize that that arc, ARC, means inverse, whether it's lower or uppercase. Okay, so those are all synonyms. Recognize those. Recognize that they mean your graphs. And it's just new notation with all the same meaning. And that's it. Have a great night.